Hi, in this video, we're going to continue Chapter 8 PowerPoint slides from Fundamental Biostatistics by Bernard Rosner. All right, so first thing we're going to do, we're going to look at the treatment of outliers. All right, what is an outlier? An outlier is an observation that is atypical compared to the rest of the data that we have. So here we're talking about just one variable at a time. So, let's say I'm collecting height and I end up going through and while I'm collecting my data about people's height, I just by happenstance get, the tallest man in the world in my data set. Now, he's going to be so tall that he's probably going to throw off other parts of my data, especially if I have a small sample size. And so any statistical analysis I would run with the world's tallest man in my height data probably is going to get thrown off. And so what we want to do, we want to first and foremost identify which observations are potentially outliers. And then second, we want to do something about it. All right, so what can we do about it? Well, first thing we could do is nothing and just leave it as is. It's still good to know that you have outliers in your data. Now, this is a very common thing to do because if I go through and start filtering my data, people may disagree with my choice to filter the data. They may think that I'm tinkering with it. So I could leave it in there and just I know what's going on. Another possibility is to remove the observation from the study. Now, that may be good, that may be bad, depending on what you're doing, especially if I'm in a small sample that could, cause some problems. Another option, and I choose this while I'm doing machine learning, by the way, is to go in and if I have extremely large value, I'll replace it with a large value from the data, but not as big. And so I'll find if I have extremely large value, I might find the observation number that's greater than 95% of my data and take that value and I'll replace the extremely large value with it. So we'll replace the extreme values with other extreme values, but not as extreme. This is a good idea if I'm doing machine learning with neural networks or if I'm using a regression model. If I'm using a tree model, it honestly doesn't matter. I don't need to worry about numerics in that manner. All right, so outliers can have a huge impact on the conclusions of our study. It's important to identify the outliers. Even if we don't remove them, don't change them, don't do anything about it so that we know what's going on. All right, so here we're only going to talk about one type of outlier, and this is the single variable type of study. And what we want to do, we want to look at ones that are far from the mean of the variable that's being measured. Okay, so if it's far from the mean, that's an indication that it might be an outlier. All right, so what we're going to do, we're going to quantify the extremeness of a value by the number of standard deviations it is from the sample mean. And we're going to call this the extreme studentized deviate. And so what we're going to do, if I have my data set and I'm worried about there being an outlier, I'm going to take first I'm going to compute the mean. I'm going to subtract the mean from every single observation, take the absolute value, then divide by the standard deviation. All right, so this is my extreme studentized deviation. And this is a single number for the entire data set. If I was to look at this without the max, that would be kind of like an extreme measurement of each observation. And so here, observations closer to the mean will be closer to 0, and observations that are farther from the mean, left or right, will be larger. All right, so let's take a look at the data we have here. So notice that here is the median of my box plots. Here is the stem and leaf plot. Here's the median. Here's the minimum value, the maximum value. And, maybe this minimum value or maybe this one's maximum and this one's minimum. Maybe these are outliers. Specifically like this 13 is pretty far from the center of the box. looking here, maybe this observation might be extreme. Like these are far enough out that I might want to take a look, might want to see what's going on with these. And here's some other data, and we can see that we have a point here that's pretty far from central tendency. Here we have a point, and here we have a point that's farther from central tendency. All right, so here we're going to do the ESD single outlier procedure. The idea here is I'm going to go through, I'm going to look at my data. What is the most extreme value in terms of deviations from my sample mean? And I'm going to ask myself, is this an outlier? If I consider an outlier and we choose to remove outliers for the study, I will go ahead and get rid of it. Then I'll repeat the process all over again and keep on going through and potentially removing more observations. Now, if I have a small data set, it's not reasonable to remove very much data. If I have a large data set, I might do this over and over and over until I have no outliers. All right, so suppose that we have a normally distributed random variable data set, and we feel that there are some outliers present. Okay, so we want a hypothesis test. I want to see, is there an outlier? Yes or no. If there is one, I want to do something about it. So the null hypothesis is that there are no outliers present versus the alternative that the outlier is present with a type 1 error of alpha. So I'm going to go through. I'm going to take the sample average, subtract the sample average from each observation, take the absolute value, and then divide by the standard deviation for every single observation I have. And then the maximum is going to be my test statistics for the hypothesis test. All right. And so now, after I get this test statistic, I'm going to look up the distribution to see if this is large, yes or no. If my test statistic is larger than the cutoff value for my sample size and my type 1 error risk, I will then reject the null hypothesis in favor of the alternative. I will conclude that the most extreme observation is an outlier. If I fail to reject the null hypothesis, then we will say that there are no outliers present. All right, and so then we're going to, keep on doing this. So if I go through and I remove an observation for being an extreme outlier, I'll repeat the process again until I have no more outliers present. And so we'll just keep on doing this. This is just basically saying repeat this over and over and over. Something that's important to be mindful of is that every time I remove a data point, my sample size has shrank by 1. And so I get a new cutoff value for here, for this ESD, and then type 1 error risk tolerance, and then sample size. And so this will shrink down my data to observations that I believe are free of outliers. All right, so in the previous data we looked at, we can see that the observation number of 13 looks like it is an outlier, but after removing 13, the rest of them are not. And so now what to do with this? Well, depends on who my audience is, depends on what they feel is the correct thing to do. So option number 1 is do nothing and run through the analysis where I know that this was in there. Option number 2, remove the outlier, and I will report that I removed that point and I justify why I removed it. I will say that the ESD was statistically significant, therefore I removed the outlier. Another thing, if I was doing a machine learning problem, I wouldn't do this for hypothesis testing, I wouldn't do this for a scientific study. I would replace the value with a different extreme value that was not as extreme. The reason why I would do that is that the extreme values can pull the model towards themselves when I'm doing regression and when I'm doing neural networks. So to protect myself from that possibility, I would do imputation, replacing that value with a less extreme observation. And so if we were to go through the slides, we could go back and look at the difference. Things look cleaner. You'll notice that when you do this, when you remove outliers, your variance tends to drop down by quite a bit. Sample mean tends to be closer to central tendency of the rest of the data. All right, so now the next thing we want to talk about is estimating sample size. So I've got a study that I'm going to do. I have not started collecting data yet. I'm going to go out, I'm going to collect data. I need to have a game plan to know when do I have enough data so I can stop. All right, so what do I need? I need estimate of variance for the populations I'm dealing with. I need a type 1 error risk tolerance, type 2 error risk tolerance, and a level of difference in the population means I need to be able to detect. What I'm going to do, so here we're going to be talking about for comparing two means. I've got two different means that I'm going to be evaluating. So I've got population 1, population 2. I want to run a test to see, do they have the same population mean aspect. So I need an estimate of the variance for population 1, the estimate of the variance for population 2. I need to set my type 1 error risk tolerance. I need to set my type 2 error risk tolerance. And I need to establish what is how sensitive do I need to have my t-test for? All right, how big of a difference do I need to be able to detect? With all these components, I drop this in. Here, you notice I'm using Z, that's standard normal. Drop it in, and then boom, I'll get the N. So the number of samples I need for the test need to be at least this big. If it's bigger, that's fine. It's even better. All right, so now, if we're going to be comparing the means of two normally distributed samples of unequal sizes. So the previous one, we had equal size. We're using a two-side test. Here, I just need to modify this, is that here you'll notice that we have the second population variance estimate divided by K. Here we're multiplying by that. And so once again, here is my difference that I need to be sensitive to. And K is equal to the ratio of samples that I need to get. Now the power for comparing the mean of two normally distributed samples using a significant level of alpha. So remember, alpha is my type 1 error risk tolerance. To test the hypothesis that mu1 is equal to mu2 versus the alternative that they are not equal for specific alternative where we're saying the difference is at least this big, then here I'm going to take the normal distribution and I'm going to take the negative z of 1 minus type 1 error risk tolerance plus that delta divided by the standard deviation of unpooled variance. And then this gives me the power. So this is the amount of area underneath the normal curve to the left of this cutoff. Now, sample size estimation for longitudinal studies. Longitudinal studies often involve comparing mean changes scores between two groups. And so here, it's going to be the ith subject in the control group at baseline. And here, this is the ith subject in the control group at year 1. Notice that it's the ith subject. And so the I indicates the subject. The first subscript indicates which measurement it is. And so here, we're trying to detect the difference on the same subject in the control group. And here we're going to say that sigma 1 is the variance of the baseline of the control group, and sigma 2 squared is the variance of the 1 year later measurement. And so the variance between these two, the variance of the difference, is going to be the variance of the second observation plus the variance of the first observation minus 2 times the correlation between the measurements times the 2 standard deviations. And this will be the variance of the difference. And so now what we're going to do, so the sample size needed for longitudinal studies, what we're going to do, we're going to take that variance of the difference, multiply by 2, and then I'm going to get standard normal for my type 1 error risk tolerance, my type 2 error risk tolerance, and then I'm going to divide by delta. This was a triangle delta. Now it's a lowercase Greek delta, and this will be the level of difference between the averages that I need to be able to detect for this hypothesis test. And then the power, very similar to what we had before, is that when I run this test, I want to know the power of the test. And once again, I'm going to take the normal distribution. I'm going to take the area under the curve to the left of this cutoff, where this cutoff is negative z of my type 1 error risk tolerance. And then I have square root of sample size times that delta divided by standard deviation times square root of 2. And here's a flow chart showing how to tackle which test to use at what time. So I've got problems. I've got 2 samples to work with. How do I navigate this? What do I do? This gives us a flow chart to go through and figure out what is the best course of action. Well, that's all I've got for you. Take care and goodbye.